All right, Peter, take it away.
Okay, welcome back, folks, or welcome if this is your first of these talks to C++20 in Chromium. This is part 4 of 4, the final stretch. I called it Comes with Caveats, mostly because I couldn't think of a good title. This is the talk for the bits of C++20 that Chromium doesn't allow you to use, at least not directly. But hopefully that doesn't mean these are irrelevant. One of them, the first one, you can use in modified form. We'll talk about why that is. And the rest of them, you might be able to help us use someday. So maybe one of these will pique your interest. And then, as with talk 3, I have an appendix with a bunch of random stuff that wasn't important enough to bring into the main talk. So in case there aren't enough questions to fill out the time, we have yet more esoteric things to go over. So let's jump in with spans. And these are by far the most commonly useful thing in this whole talk. Not everybody has encountered these before, so if you already understand spans well, I'm sorry, the next few slides are going to cover some familiar ground for you, but maybe it'll be a good review. A span is a window into one or more elements that somebody else owns. And I spent many years in Chrome not understanding this kind of a type. Like, string view had a predecessor in Chrome code all the way back in 2006 called string piece, and I never knew when I was supposed to use string piece or not. I did not figure it out for years. So if that's kind of how you feel with things like string view or span, then maybe this table that I'm showing, it will help you to sort of figure out the relationship of these types. So just to cover what this is, if you're thinking about the memory that's associated with some type, think of two facets of that. One is whether you've got one element there or potentially a whole series of elements, and the other is whether the type directly owns the memory in question or whether it's just referring to memory that somebody else is managing for it somewhere else. So you can make other distinctions, stack versus heap, const versus mutable. I don't care about those. In this case, these are the two that help me understand these type relationships. And the left column, the owning column, is generally the column we teach new programmers first, because these are just fundamentally kind of easy to understand. They work often like values. You can pass them around. When some of you may be saying, like, wait a minute, like, why did you put string in the multiple elements owning column? Like a string is a one thing. Here I'm thinking a string is a series of one or more characters, and it's the actual characters that are the memory in question. So you've got a string of characters or a vector of t's or something. But like, these are types that people can generally use successfully, and they very quickly encounter one of the fundamental problems with these, which is that they're potentially expensive to copy. You generally are going to have a bad time if all you ever have is these and you pass them by value everywhere. Of course, we have move semantics, but that still doesn't cover all the sorts of ways that you might want to use these. What if you want to give out shared access to a single copy of some kind of data? And that's where the right-hand column comes in, the non-owning types. Fundamentally, at the core level, all of these are built off of pointers under the hood. So they all have some level of indirection compared with a basic type, but it also means that they can be copied and passed cheaply because the cost of copying or passing them is about the cost of copying a pointer instead of all of the data, potentially. And you can have multiple instances all pointing to the same underlying copy of the data. So this is good for certain use cases, but it also has clear downsides. If somebody changes the underlying data, then what you're reading back can change out from under you without your notice. And more worrisomely, they lead to memory safety bugs if the underlying data gets destroyed or if they allow you to access it beyond like the range that the data actually exists in. So we get dangling refs, out of bounds pointer accesses, and these are like kind of fundamental worries with all of these types here. So spans mitigate the out of bounds access risk by holding not just a pointer to the underlying data, but also a size. You can kind of think of this a little bit like an array that doesn't actually own its own data, like an array ref or something. So with our hardened libc++ implementation, they bounds check all of their accesses against the size, which means that if you attempt to read or write out of bounds, then instead of getting a memory safety bug, you get a crash, which is deterministic. And because you can read the size off of the span, it's available through the API, it also makes them an ergonomic replacement for anywhere that was passing like a pointer and a size, which is really common idiom for C APIs. Or worse, if it just passes a pointer and it expects the callee to like know what size to use, or maybe to like look for a Terminator character or something in the memory. Now, that means that spans mitigate one kind of memory safety bug. They don't mitigate the other kind of safety bug. You can still have use after freeze with spans if you're holding a span beyond the lifetime of the object it's referring to. But it does mean there is strict improvement on doing pointer arithmetic. And we have an open project because of that to convert the whole code base to use them. There's a migration bug here. There's also another benefit of spans that I talk about a lot in code reviews that I do, where I advise people to use spans, and that is that they make functions agnostic to what kind of type is actually owning the data under the hood. So compare the two functions I'm prototyping here at the top of this slide. I have takesVec that takes a const_vec ref, and takesSpan that takes a span by value. Now, both of these are pretty cheap to call because calling it is going to involve passing like a pointer, and in the case of the span, a size. They both give the called function read-only access to some contiguous block of ints. And if, like in the first calling block here, we actually have a vector on the call site, then both of these generate very similar assembly code. If we don't, then the span version is better. So in the second caller here, instead of passing a vec, I'm passing an initializer list. Now, it turns out that doing that is expensive when you pass it to a const vector reference because we basically have to construct a vector at the call site and then copy in all of the args from the initializer list and then pass it. And the span version, while it doesn't work until C++26, is very cheap because it can pass the initializer list thing directly. The C++26 part is because std_span doesn't actually get an initializer list constructor until C++26. In the third version, when you're passing a C-style array, the vector version won't even compile, but the span version still works fine. Who cares? Why is this useful? Well, if you've tried testing APIs that take like const references to things, you've noticed that it often forces you to use things like vectors where you could have just used initializer lists or other kind of inline constructions. And more semantically, if you think about this in terms of my second talk, the one on preconditions and constraints in templates, the issue here is that functions like takesVec are actually over-constrained for what they're trying to do. What they need is read access to a block of ints, but what they're asking for is a vector. The span version is actually saying much more directly, I need some block of ints that I can read. So it's expressing semantically what its precondition is in a more precise way, and that lets the compiler be more flexible, either more efficient or to call it in more cases. And it makes the code more maintainable because in the future, we can change the call site container and we don't have to touch the callee. And if you have actually had to change like deep viral APIs that used to be taking a this container and now need to take a that or something, then you will understand the utility of this. So the big catch with spans is that in Chromium, we don't let you use them. You can't use std_span. You need to use base span. Why? Why did we have this? Well, for one, std_span didn't come around until C++20, and we recognized the need for this quite a few years ago. So base span was, at the very minimum, a backport to previous versions, and we've had it for a while. That's why probably a lot of you have encountered spans before, maybe have encountered them quite a long time ago. But there's other issues that make us stick with base span and not say, oh, now that we have std_span, we'll just migrate to it and get rid of the base one. The First thing is, you'll recall I mentioned earlier, non-owning types can have use after free issues, and that STIDSpan suffered from this. Basespan also suffers from this. It's not perfect, but it's a lot better because we've added at least 2 different layers of lifetime annotations to Basespan to try to help Clang warn on spans that outlive their source data. So at least some of the lifetime bugs that you could potentially make with a STIDSpan, you can't make with a Basespan. Basespan also has ergonomic improvements over STIDSpan. The initializer list thing that I said, oh yeah, you can't get that until C++26. Well, actually you can today in Basespan because I added it. Basespan also has a bunch of convenience functions that STIDSpan doesn't have for like splitting off pieces off the front so that you can, loop through and chunkify a span or copy it or compare it. And collectively, all these changes mean that we're not likely to ever use STIDSpan directly. We're probably always going to stick with the base version. But Basespan does convert implicitly back and forth to STIDSpan. So if you have like a boundary between third-party code that's using STIDSpan and Chromium code, then no problem. You can just basically convert from one to the other at the boundary, and it will be cheap. So spans, go forth and use them. They are awesome. Next up, STID format. STID format's a new text formatting utility, and really the primary use case of this was for code bases that were using sprintf, which is a long-standing function that lets you format using printf style format strings and write into a character array buffer. It's kind of nasty to use because you have to like pass the buffer in and do stuff like that. Slightly more ergonomic in some cases are string streams, which have also existed for a while, but unfortunately streams of all sorts generate really inefficient code in a lot of cases, and it's questionable whether they are actually like nicer to use and more ergonomic, depending on what you're trying to do. They can be very verbose. So Chromium, for a long time, has had an alternative to this called string printf. We'll talk about that more in a minute. But what I'm showing you here is the C++20 answer to all this, which is STID format. If you're a Python programmer, this will probably look fairly familiar. STID format uses these paired curly brace substitution points that you can write into the string with. And unlike with printf, you don't have to specify what type of object goes in there. It's more like using streams where you just say, and then stream this thing out, and it just works. So here, hello world, when you STID format with hello brace brace. If you do need the power of printf, you can put format specifiers inside the placeholders. You can put things into control like padding and width. So it's still possible to do everything printf can do. It's just often a little easier to use and certainly nicer in terms of the type safety and stuff. Now, I mentioned Chromium has string printf. String printf used to be kind of our own implementation. It's under the hood. It's actually currently a wrapper around Absol's stir format. That's potentially subject to change, so that's the reason why we haven't just actually replaced all the calls to string printf with stir format. And string printf brings you a lot of the same benefits as STID format, which is that it's about as fast as printf, it's more compile time safe, it's ergonomic. STID format is clearly a win over string printf, though, because the string printf still forces you to specify like %d, %l, whatever you're going to do, whereas STID format is just curly braces everywhere. So we've talked about, well, maybe we should cross-migrate. Like, should we go from string printf to like STID format? It turns out there's a Clang tidy migration path that can actually do this sort of migration for you. So it probably would be practicable to do this, which it clearly wouldn't without tooling. But there's a big problem with STID format, and that is that there's a third-party library out there called formatlib. It's often spelled curly brace fmt, curly brace. which is just better than std format in every single way. In fact, format lib is where std format came from. Format lib was the basis for the standardization of std format. But since std format was standardized, the format lib maintainers have continued improving format lib rapidly, which means that by now format lib is faster to compile, generates faster code at runtime, and generates like much smaller assembly code compared to std format. Part of this is just because like C++ library maintainers have a lot more to do than just optimize their format implementations. So their attention is split all over the place, whereas format lib is very focused. And thus, if we ever wanted to switch to std format, the question is like, well, why wouldn't we just switch to format lib? Like, it's everything that std format is, but more. Furthermore, the advantage of not having to write like %d or something over string printf is arguably not that big. Like, I mean, yeah, it's kind of nice, but is it worth switching the whole code base over? We're also worried about whether std format and the like actually cover all of the same kinds of errors that you can do and catch them at compile time. So the upshot of all this is that std format itself is almost certainly never going to be used in Chromium, but we would be very interested in knowing kind of like the answers to these trade-offs for format lib. PBoss has experimented some with format lib and like check and decheck to see if we can get rid of streaming there, because that's one of our big uses of streams. Lessix over on the V8 side has asked the ATLs if they can use format lib, because V8 like kind of doesn't have string printf or really a good standard for doing a lot of this stuff. And it would be very interesting to us if somebody wanted to go like actually like do a local change to, I tried pulling in format lib and just like changing a huge swath of Chrome code, like all of base or all of I don't know what, using that like clang tidy migration pass. And it worked, it compiles, and here's the actual, you know, compile time and binary size impact. So if you want to do that kind of work and you want to propose something to us, if like you know things about format lib already or this is your bag, CXX@ is probably the right mailing list to talk to here. We would definitely welcome you. Robert asks, does it convert the given type to a string using the ostream operator or something new? By it, I assume you mean format lib. It does not use stream operators. So if you want to do custom type conversions with format lib, there's hooks to that you extend to tell it how to format your custom type. I won't go into the details of that here, in part because I don't remember them. Don't tell anyone that I didn't know everything about C++. But also because it's kind of beside the point. Is that true for std format as well? Yes, std format and format lib have almost the identical API. Like they're very close in terms of their usage pattern. So std format, in case you were excited about it, probably get excited about format lib. Ranges. You're like, wait a minute, we already talked about ranges. You talked about them in talk 3. Well, I talked about the algorithm side of ranges, but there's actually a lot more to ranges, specifically range views and chaining. So range views are, in my opinion, misnamed because they're not precisely view types. If you are a programming languages nerd and you have an idea of what a view type is, that's not quite the same as what a range view is. But usually they're non-owning, they're cheap to copy, and their basic purpose in life is to lazily provide access to underlying elements of some input, usually transformed in some way. Maybe you filter it, maybe you transform it, maybe you extend it, maybe you, I don't know what. So there's an example of some code here that I'm showing. I mean, obviously this is like kind of arbitrary and constructed, but just to show off some views, you have like views iota that generates numbers, in this case from 1 up to, but not including 10. You have filter that drops elements out of the underlying range. You have transform that modifies the values of the range. And then you can see we've chained them together here with the bitwise OR operator, which almost all of us will be familiar with from like Unix-style pipe usage on the command line. Now that's been brought into C++ here and overloaded to mean like chain these operators together sequentially. And people who come from functional languages are like, yes, finally C++ can do the most basic of things. Whereas people who like grew up programming in C are like, I have no idea why you are ORing together all of this stuff. Like, this is just bizarre syntax. But you can kind of understand the appeal of being able to write very simple chained transforms of things and having a bunch of them freely available in the standard library for you already. This is useful in certain cases when you have like a data-oriented pipeline that you just want to implement using a couple of different operations. So, I mean, why not allow this too? Because we don't. We ban this. Why? Well, there's a lot of reasons. I'll try to cover them kind of quickly. The first thing is that when you start using these a lot in your code, your compile time explodes. Part of this is because of the way that operator overloading lookup works and how the compiler has to like increasingly look through thousands and tens of thousands of potential overloads for things every time it does stuff. Part of this is because of template explosion. So compile time takes a noticeable hit when you use these. This results in a lot of intermediate code. Now, whether that results in a lot of code in your final binary is much more dependent on your optimization settings and how good your compiler is and exactly what the code is doing. But certainly it makes the compiler's job faster and easier if you don't generate 10 billion lines of IR for it to optimize away. There's a lot of concern that this is weird stylistically for people to read. I personally am not as sympathetic to this concern, mostly because there's already so much syntax in C++ that, like, if you can read everything instantaneously, you're amazing, and I kind of already expect that people encounter code that they don't really know how to read. But it's clearly, like, adding yet another way of spelling stuff to C++ doesn't make people's lives any easier. There's some concerns about how, when I said lazy access to the underlying thing in views, that there's like a lot of potential gotchas underneath that. Like, well, if it's lazy, what happens if, like, while you're evaluating it, the underlying data goes away? Or what happens if, like, there's a chain of 50 million, like, n-squared things underneath that, and so as the size of the input data increases, like, stuff blows up? I don't fully understand all these concerns because I have not read deeply into the debates over this, but I've definitely seen a lot of, like, debates over you really need to stay away from X, Y, and Z, or it turns out that making this obey all of the properties that we said it had to have is really hard. Ellie mentions that laziness can definitely be a huge deal in Haskell, which I'm like, you clearly have spent more time in programming languages classes than I did because you've used Haskell. All I know about Haskell is like something about a lambda symbol, so I'm clueless. One of the biggest worries, though, with ranges is that C++ really doesn't have a good language evolution story. For the past umpteen years, we've kind of baked both API and ABI concerns into the library and said we're not really willing to change them. So if we land something in the standard library that has problems, we're stuck with it. People who work on the web platform are very familiar with the problem of you landed it once and now you can never get rid of it. And the web platform is actually more evolvable than C++, which is sort of sad to me. But like std-regex is kind of a poster child for not a fundamentally terrible idea, but it has some problems that we could fix, except we're definitely not going to fix them. And it's just forever kind of going to have problems. So this is the concern with ranges, is that like all of these giant changes to do ranges kind of crash landed into C++20 at the last minute, and now we're kind of stuck with them, and even if it turns out to be problematic, we can't fix them later. So for all of the above reasons, which is a lot, these are banned by the Google Style Guide. And we probably won't ever allow these parts of ranges either. That's sort of sad, because there are legit use cases that this really does make better. And so for some of those, we've added things in base that like carve out particular use cases, like a view that transforms whatever your input range is into a vector. That's very useful. So we have base 2-vector. A view that converts all of the things in the range to R values. We have base range as R values. So like when you encounter specific use cases that you would like to use ranges for, but we don't have a good idiom for them, I think base maintainers would be very open to considering, like, should we add another thing to base to let you do that in Chrome in a one-off way. For larger parts, there are alternatives to ranges, because a lot of other people have noticed these concerns and have written their own things. In fact, so many things that I have no idea what the trade-offs of all of them are. I'm linking several here. Repel is kind of the Google one that's being worked on, and that's been talked about publicly, but as far as I know, not open sourced. There's all these others that I've seen mentioned on the C++ subreddit. If this is your bag and you're like, I want to know more about the alternative to ranges and propose something in Chromium because I think some of these are cool, looking these up, doing research, finding out what the trade-offs are and saying, like, we should use this and here's why, super useful. I would love to see that. So once again, contact CXX, the generic mailing list for all style and language evolution questions in Chrome, if you want to propose something. All right, and now we get to the two things that really don't have any immediate route forward: coroutines and modules. So coroutines first. Coroutines are basically a new low-level facility to do multitasking. C++ is not the only language with coroutines, or with things that work like coroutines. There are all kinds of async constructions in other languages. I'm not a programmer with any facility in like JavaScript, Rust, like all these other things. So I'm not going to do comparisons of coroutines versus like Rust async or something, because I would just be way out of my depth. But fundamentally, C++ coroutines are basically a cross between a normal function call and a threading interface with a lot of very low-level configurability. So I'm showing the most useless possible example function here. It does something, it calls co-await on something, and then it does some more stuff. There's nothing abnormal about the code elided for point 1, like it's just normal function code and it doesn't need to do any special setup or anything. At 2, where we call co-await, the something here might look like a function call, it might look like an object, but whatever it is, it's something called an awaitable, and it implements a special interface that tells the compiler what the compiler should actually do when you try to wait on it. The waiting generally involves suspending the current function and then saving off its context somewhere. This all happens under the hood for you. And then it might involve invoking other functions, starting other threads, waiting on other objects. Can be very much up to the implementation of this awaitable. Then eventually, somewhere down the line, someone is probably going to terminate that execution, usually using the new keyword co-return. Not always, sometimes they might use co-yield. But co-return will basically, like, it's the return equivalent in coroutines land. It will return back up the stack. The compiler will restore all of your state. The function will continue executing at point 3, almost as if nothing ever happened, except that depending on what the awaitable did, it might be now running on a different thread. It might be like there might be various other global state changes that have happened, even though from the reader's perspective, we're in the middle of straight line function code. So this sort of sounds dangerous or weird if you're thinking about like safety aspects, like you're running along and then suddenly like maybe you thread hop or maybe like objects like go away when you weren't looking. But this is actually very useful in a lot of contexts. If you think about code that passes continuation functions along everywhere to a lot of like, hey, do this, do this, do this, and then like come back and continue here, you can rewrite a lot of those as just straight line functions. And in a lot of these cases, you can actually get rid of entire classes that were just used to save state, because now all the state saving is done by the compiler for you. So for certain types of use cases, coroutines are extremely compelling in making your code shorter, much more readable, easy to reason about, often safer, because like you're not trying to preserve state and then having to worry about object lifetime or something. So there's a lot of good reasons why many people have been very interested in this. Coroutines are solid enough that Google 3, which is Google's internal code base, has been rolling out a production quality interface called C9, I believe. So how might we use this in Chrome? Well, I already mentioned that we might augment or even fully replace posting tasks with this. Somehow, you could imagine turning a lot of like post task and reply or something into some kind of a co-await. Or we might use this to create some kind of new promise or future style API. Promises and futures not only being familiar to JavaScript folks, but actually these are part of the C++ standard. There's like std promise, std future. We don't use these because they're heavily tied to the underlying standard library threading model, and we don't allow that because it's not really compatible with our sequence, the sequence runner stuff that we do in Chrome. But the idea of like promises and futures, of being able to say like, hey, like here's this promise, and you can like wait on it when you need to actually get the answer from it, is compelling enough that this has come up before. 5 years ago, there was a proposal in Base to do promises, and it went a long way down the road, and eventually tech leadership decided not to proceed with that. But maybe we should revisit that. Like, do coroutines provide a like more performant or more flexible or more maintainable implementation of it? Or like, can we solve some of the other concerns that people had at the time about promises? So in fact, there's actually a meeting I'm going to be in later this week where one of our external contributors from Brave is going to be presenting to several people inside Chrome on the coroutine-based promise implementation that he's proposing that we do in Chrome. And there's also been discussion on CXX from Eric Jensen about yet another way of doing coroutines in Chrome. Eric's going to be part of that meeting. I'm kind of hoping the two of them will like hash out together like how should we go forward, because there's unfortunately a lot of complicated things to work on here. One of the issues with coroutines is that the primitives are very low level. I did a ton of hand waving several slides ago when I was like, well, you co-await something and it might be anything and it might do anything, and like that's not very descriptive. But the reason I can't be specific is because the configurability basically boils down to, yeah, you write these classes and then they give you some functions you need to fill out and you do whatever you want in those functions. And if you happen to step wrong and blow up all memory or cause an infinite loop, well, too bad. I spent quite a few weeks reading through other people's coroutine explanations online, stuff from like Raymond Chen and like all kinds of like coroutine libraries, and trying to figure out how coroutines work. And let me tell you, this stuff is not easy to just understand and do right. There's a lot of gotchas and there's a lot of implications in how you design your APIs. So this is going to require some extensive design. The safety story here, as I kind of alluded to, is unclear. Like, there's reasons to believe these might make things less safe, and also reasons to believe they might make things more safe. The desired API is uncertain. Even if we come up with something that makes Chrome a lot easier to use, can we actually migrate to it? Are we going to end up in a world where now, instead of posting task, we have like post task and this other thing, and you get to choose between them, which I would kind of feel sad at because we already force developers to make way too many choices, and like say, well, you need to learn yet more in order to do your job. Would be better if we could come up with like, here's the one true path. This is what you should use, and this is why. But that's unclear whether we can do that and can migrate. Unfortunately, even though I said this was mature enough for Google's use, the tool chain is still buggy. LLVM's release notes say ABI and stability issues on Windows. Well, guess what platform Google 3 doesn't run? Windows. Sadly, we do run on Windows in Chrome, so we care about this. And when I prototyped a port of some of their stuff over to Chromium to see how it worked, it mostly worked and then had a few cryptic failures on a few platforms, which is kind of what I would have expected if there are toolchain bugs that Google isn't hitting. So what is the status? Well, I mentioned there's that meeting later this week, and we're kind of very much in like figure it out API proposal. What do we want to do? We're definitely not going to have a usable prototype any earlier than like late this year. Probably it'll be later than that. But if you're super keen on this, Gab is the person who's coordinating this effort. He's probably overloaded already, so I don't know exactly what he will do if there are hordes of people beating down his door, but coroutines are definitely an area that the future is very much like an open field of we're not sure what we want to do and how. So you could contact him to contribute. Okay, and then modules. My second test audiences were like, wow, I hate modules. These suck. Let's never use them. And then like later that day, somebody else said to me like, oh, you're talking about modules? Good. Modules are great. I love modules. So, all right, we got both opinions here. Let's see which one you fall down on. Modules are basically a new system for organizing your code. Since the days of C, we've had source and header files, and then we've had kind of ad hoc build systems ranging from shell scripts and make files all the way up to very complicated things with Blaze and Meson and, you know, I don't know what. So modules mostly do away with the need for header files by replacing a lot of the uses of the preprocessor. I'm showing a simple example here. You'll note that there are two source files, but there are no header files. In the first source file, we say export module, and then we export the symbol hello below that. So what we're doing with this is we're basically creating a module. Well, we're saying that within the module named hello world, we're placing this function hello that does this thing. And then in main, where we say import hello world, which feels very Java-esque to me, we now pull all of the symbols from hello world into scope. So now we can reference hello, and it will use it from the hello world module that we contributed to up in helloworld.cc. You can split modules across source files. So you can have a single module that has pieces contributed to it from various source files. So we could imagine having like a module for, say, all of base. And then instead of like pound include these 15 source files from base, you would say import base. And now you have like all of base. You can still do namespaces inside modules. So you can still like leave things like scoped and organized the way you want. But now the advantage of this is that because you're not pre-processing and running the compiler on the transitive closure of all your headers in every single CC file, and instead you're like compiling this module into like a single compiled object once and then sort of pulling it in when you need to compile from it, you get the benefits of, say, pre-compiled headers, but perhaps even more efficient because maybe you can go farther than a pre-compiled header can go. In fact, I believe that whoa, did I skip a slide? Yes, there. I was thinking like, hey, I'm anticipating my next slide. You can control your symbol visibility without saying, well, everything that we need to make public needs to go up into the header file and all the private stuff can stay in the source file. You just put it all in one and just choose what to export. And there are potential toolchain benefits. Like Toolchains today have to do a lot of recompilation on the fly continually while you're typing or doing stuff in order to know what's even going on. But with modules, potentially a lot of the state of the world can be on disk or in memory available already, and this might make our toolchains, do I keep saying toolchain? Like code editors, IDEs, other things like that, faster, more responsive, more intelligent, etc. I am hand waving, and I will get back to that. So modules potentially have a lot of benefits here. What's not to like? Well, if you want toolchain immaturity, then modules are the poster child for it. Modules today in 2025 are still basically not ready for production use. And I say this partly because of our own experience with it, but also partly because I'm watching out in Reddit and various places online, and there are lots of stories of small hobby projects using modules. Pretty much no stories of major production teams using modules on big projects. The one notable exception is Microsoft Office, which has written some public blog posts saying, hey, we're moving to modules, here's our progress as we go. That's very interesting. I'm reading their blog posts for sure, but they're still in kind of early days along that way. The last post that they had was still very early in that process. There's a lot of questions here on the build system side. You have to implement support for modules in your build systems because when the compiler outputs these intermediate results of compiling to a module, the build system needs to understand what is that artifact? Where does it go? How do I pass it on to further stages of compilation and linking? What is it named? How do I find things, etc.? And so every build system has been wrestling with this. CMake implemented support for modules, and then Meson immediately came out and said CMake did everything wrong and you shouldn't do anything like that. And then a flame war erupted, which was kind of entertaining, and I got popcorn. But we use GN, which nobody but Chrome uses, which means nobody's going and implementing this for us. If we want to use this, we're going to need to implement the support for it ourselves. So that's yet more work that's going to have to happen before we could do this. The actual benefits of modules, I sold the exciting story on the previous slides, but in reality, it's very much question marks. MS Office, which admittedly is not parallel to us because they had a very heavily precompiled header optimized code chain. We don't use much precompiled header stuff. There's a little bit in Blink and pretty much nothing otherwise. But they're finding some cases, speed up by 90% and other cases slow down by 9,000%. You're wow, okay. So it's not clear, not only what the compile time effects are, although everybody thinks that the overall effect will be positive. I mean, precompiled headers are positive, and these should be at least comparable to that, probably. But it's also sort of unclear what the disk usage and memory bandwidth and whether any of those IDE benefits will actually materialize. There was a lot in there about oh, we could make our IDEs faster and better. Well, will we? And can we? And I don't know. I mean, you don't know until it's actually done, and it's not done yet. So both Google and Chrome deprioritize C++20 modules in part due to all this skepticism. There's yet another reason why Chrome has not been keen on modules, and that's because we are Clang only, and that means we have access to Clang header modules, which are a non-standard Clang only thing that predated C++20 and give you some of the benefits of modules pretty much with none of the porting costs of modules. So we're experimenting with those right now to see if we can kind of get that for free. That makes it even less compelling to put a bunch of energy into modules. Migration, if you do want to do C++20 modules, is very non-trivial. You can do it in trivial ways. You will not get the full benefits. There was some debate between STL, who's one of the maintainers of the STL implementation at Microsoft. Stephen, I don't want to try to pronounce his last name because I'm probably going to butcher it, but Lavave or something like that. And and one of the other tools folks like working on module stuff about this, but my impression is like, hey, this is not a trivial thing to do, in particular because modules don't support macros. And so if your use of the preprocessor included macros, then you either need to like keep it around for those and port the rest of the stuff around it, or you need to figure out a new story that doesn't use macros, which I've done some of in Chrome, and it is feasible in many places, but it's certainly not trivial. The upshot of all of this, C++ 20 modules, I'm just like going to pull a number out of the hat here and say we're not getting it before 2 years from now. I just don't see a way, because nobody's even going to look at it before next year at the earliest, and it's going to be a big slog after that. Clang header modules, on the other hand, we might get. We might get those fairly soon. Julian notes Clang header modules basically removes all the code readability improvements, by which I assume you mean, Julian, that we fail to get the C++ 20 modules readability improvements, which is true, but hey, I will take a free compile time speed up with, you know, a lack of other benefits where I can get it. If you do want to experiment some with all this stuff, be it header modules or real modules, Eric Staub is probably the guy to contact. He is head of a lot of the tooling efforts. So I would contact him with this. So last thing on my agenda, I want to kind of bookend this series. I mentioned very briefly at the start of the first talk, like, why am I not talking about C++ 23 now that it's or now that it's 2025? A single slide on C++ 23, just in case you wanted to know like how it fits into all this. There are a couple things that we would need to do in order to go ahead and move to C++ 23. They deprecated aligned storage, which we've already removed from all of Chrome, but is still present in some of our dependencies. Victor Viana has been doing awesome work, slowly knocking those out of dependencies and then rolling them from upstream. So contact him if you happen to want to help with that. Unique pointer got a lot of its API got made const expr, and that means that now the compiler can suddenly diagnose a whole bunch of usage that I'm pretty sure was either UB or ill-formed, no diagnostic required, one of the two. C++ is so exciting that it has multiple ways to spell you did it wrong and we're not going to tell you about it. But I think we had previous usage of like unique pointer where the template type that you're operating on is only forward declared. It's not actually fully defined at that point. You can do that, but you can only do that for very limited usage of unique pointer. As soon as you start calling any of the APIs, you're supposed to have a fully defined type. And we didn't, and now the compiler like diagnoses tens of thousands of errors in Chrome. We'll have to fix those. Luckily, the vast majority of those come from like a small number of files or from auto-generated code, so we can fix huge numbers of them in big chunks. But we'll need to fix that if you happen to want to fix that. And of course, rolling to a new version always requires coordination with other teams. So I've done some of this before. Nico Weber, whose username here, Thakis, is an even better contact point on that. The likely story on C++ 23 is that probably the ATLs will start trying to find somebody to do some of this work next year. If it happens to get done before that in people's spare time and we can just roll easily, like we might consider doing so. But if not, then probably sometime next year, somebody will get tasked with some of this stuff. Takeaways from this talk. I mean, it's a little bit hard to write this, right? Like you can't just take away, well, you can't use X and you can't use Y and you can't use, but you can use base span. So use base span, definitely instead of pointers and sizes, but also consider like anytime you'd pass like a const vector ref, think about whether your function really actually only needs a span. Similarly, anytime you'd pass like a const string ref, think about whether you actually only need a string view. It might be useful to pass a const ref, not appropriate to make this change in every circumstance, but worth thinking about. Another takeaway is simply that we don't allow everything in the standard. And in general, we don't allow things from past versions of the standard either. So we've got a doc called C++features.md. You can search for that in our source space. It's marked down, so like view it in Git tiles. But it generally gives the whole list of here's what's banned and why, and here's who you could contact about it. And then finally, just kind of like reiterating that almost all of this stuff, like upgrading our C++ version, writing wrappers in base, proposing new libraries, researching how to help the code base, all of this is volunteer work. I'm a base owner. Working on base is 0% of my assigned job. Like upgrading C++ to C++20, like not my assigned job. And similarly, all the other people who are contributing work in this space, like not their assigned job. This is basically all community contribution level stuff. So if that's the kind of thing that excites you, we've definitely got lots of opportunities. Certainly more than I've covered on these slides. I've linked a few of the migration bugs. Roger says, are there a set of bugs we can refer to for making these changes as we go along? There's certainly bugs on spamification of the code base, and like fixing actual like pointer to span conversions. There's at least one bug I filed on, hey, we should use string view more often in place of string ref. That's very aspirational. I don't know if there's a bug anywhere on like we should consider using span more in APIs in place of convec ref or something. Would have to search for that. So I don't have those numbers offhand. I could look them up if you ping me after the talk. Like I said, there is an appendix, but I'll stop here. This is the end of the main talk series. I hope you've enjoyed this talk, all 4 of these talks. If you feel like you learned stuff, great. If you feel confused or overwhelmed or like all of it leaked out of your other ear, that's okay. Having a bunch of info fired at you at high speed in a talk is not the best way to learn. You need to actually be repeatedly exposed to this and then go put it into practice yourself. So just a reminder for all of you internal at Google, there are Go links for all these slides, go/CPP20-Chromium-number. And you can go look back at things and review stuff that was interesting, or try finding things to put into practice and send me patches to review. I'd be happy to help you. And with that, any questions? Robert, let's take you first.
Oh yeah, I asked it in the chat earlier. I think you might have missed it. But with the C++ modules, how does it know where the thing that you are importing comes from?
All right, I see that question of yours in the chat. Yeah, I noted it, and then I went right past it and didn't address it. My answer is I don't know. I actually haven't looked at how this is supposed to work. I believe what's supposed to happen is that the build system is somehow supposed to have fed that particular like BMI or whatever it's called, the compiled module thing, to the toolchain, and then the toolchain just like makes an index of all the stuff that you pass into it. But then of course that just pushes the question one step back to like, well, how does the build system know? Like if you've got like hello.obj and foo.obj and they're both contributing to a module named bar, like how does it know like where to find that and what to contribute? And I have no idea.
Yeah, I was thinking of your example of like if you import base and use some things from base, like, does it have to just go find everything that contributes to base in the code base? And, yeah.
My belief is that some of the answers to this also vary both by toolchain and build system. That like GCC and Clang have been like fighting about how to do this, and build systems have been fighting about how to do this. None of this was like really spec'd in the module spec from the C++20 folks. Peter Kahn in the chat asks, C++ language development, what's your opinion on safety profiles? He's inviting me to like throw bombs into the room if this talk gets posted publicly. I have posted some stuff about this on Reddit, but I'm generally skeptical on safety profiles. They could potentially be benefit. By the way, if you don't know what safety profiles are, this is very much like, this is stuff that was in discussion for C++ 26, didn't make the train, and is now, they're going to do a white paper on it, and then it'll probably come back up in the 29 timeframe. But this is like pursuant to the big C++ is unsafe, everyone needs to move to a different language debates that have been happening in public, and safety profiles are a proposal on potentially how to address this. I am more on the Sean Baxter side of things that says no, if you want to provide really good tools, we need fundamentally different tools that are big major shifts, and to the way to adopt that is not by making the annotations easy to apply, but by providing automated tooling that helps people to rewrite to that direction. Carbon from Google is also an ongoing bet in this direction. To basically say hey, we need to have some story that starts with C++, but then moves to somewhere fundamentally different. That's my briefest possible take on what I think. Julian, following up on the modules question, is there a definition of what has to be found under which conditions, in BMI stuff? Again, I have no idea how technically modules are supposed to work under the hood. I have not read the papers. I'm not familiar with it. I am just ignorant. Sorry. Questions? Okay, you're welcome. There's 3 minutes left. I will quickly see, what did I even have in the appendix? Because I actually don't even remember at this point. Oh, Robert. Yeah, go ahead.
Maybe it's more of a commiseration, but you presented a bunch of really shiny things that we can't use. I was just looking up generators, and it seems like those are dependent on coroutines, which...
Yes.
Yeah.
The idea in C++ 20 coroutines where we will give you the low-level facilities, and someday we will provide high-level facilities built on them later. Generators are part of C++ 26, and they are one of the first sort of higher-level facilities to try to use coroutines at a low level to do stuff.
Yeah. Let's
see. The appendix. We only have 2 minutes, so I can't actually talk in any detail about these. But let's see. We had bitcast. Which this is, now these are all in this talk because these are all things you can't directly use. So we have base bitcast instead of std bitcast. And I had a hilarious slide here on type punning and what it is. You can just roll over laughing now. Oh, the Quake 3, famous fast inverse square root stuff. Blah, 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 blah. Wow, there's a lot of stuff here on bitcast. We had std2address, which converts a smart pointer or dumb pointer to an actual raw pointer, which you can't use. You can use base2address. And yes, if you want to know, I'm going through these in part because I'm curious and in part because I want them on screen for 10 seconds so that I can justify the amount of time I spent making these slides. There are some notes on these slides. If you go back through this talk and you read the presenter notes, you will get some of the flavor of what I would have talked about. Oh, that was the only 2 things. Okay, it was just bitcast and to-address. So much more esoteric than things like spans or coroutines or some things. There might someday be a C++ esoterica talk on no unique address, which is a new annotation that was added in C++ 20 that turns out to be a pit of horror. And I spent weeks researching because I wanted to understand how it worked. Dana Janssens, who left Chrome a few months ago, had some good write-ups on that online, and it might be fun to give a talk on that someday. But with that, I bid you adieu. Thanks for tuning in for 4 weeks or whatever you actually did, and I'll see you someday in the future.